Hello guys, and welcome to another calculus video. Today I have a really fun one for you guys. It's a relatively simple integral which we'll first solve using the normal methods, and then we'll solve using the original method that I used when trying to solve this problem, which leads us to these really cool infinite series. Through a bunch of different methods, we're going to use the beta function, we're going to use infinite series, we're going to use um, Taylor series for square root of 1 minus x, and we're going to use the gamma function. So all of that's going to be really cool. So we're going to start out with the normal method, and then we're going to dive into the wacky, super long, incredibly fun methods. So without any further ado, let's jump right into the video. So the first method that we're going to use to evaluate this is something that many of you have probably already guessed. We're going to do basic trigonometric substitution and using x equals sine of theta. Then dx is going to be cosine theta d theta. And we're going to end up with the integral from negative pi over 2 to pi over 2 of, now square root 1 minus x squared, that's the square root of 1 minus sine squared, which is square root cosine squared, which is the absolute value of cosine theta. However, since you can see on our domain here, we're between negative pi over 2 and pi over 2, cosine theta is always positive there, so we can go ahead and remove these absolute value bars. And then on the bottom, we'll have 1 plus sine squared of theta. And then we'll have cosine theta d theta. Next, what we're going to do is multiply by secant to the fourth and on the top and bottom, and you'll see why. So we're going to end up with the integral from negative pi over 2 to pi over 2. And on the top, cosine squared of theta times secant squared theta is just 1, and then we're multiplying by secant squared theta again, so we're just going to end up with secant squared theta on the top. And on the bottom, we're going to end up with secant to the fourth theta. And then sine squared of theta times secant squared theta is tan squared theta, and then another secant squared theta. Now we're going to be able to do u equals tan theta. Du is going to be secant squared theta d theta. So we're going to end up integrating from negative infinity to infinity of 1 over, now here's the fun part, we get to factor out secant squared theta and then secant squared theta plus tangent squared theta. And secant squared theta is just u squared plus 1. And then secant squared theta, as we said, is u squared plus 1, and tangent squared theta is just u squared. So we're going to end up with 2u squared in this second parentheses. Or sorry, 2u squared plus 1. Next, we can treat u squared as a quote-unquote variable in this situation to make our partial fractions decomposition even easier. So I'm just going to go ahead and use the cover-up method right here. We're going to have over u squared plus 1. We'll set u squared equal to negative 1. And then when we plug in 1 over 2u squared plus 1, we're going to end up with just negative 1. So this should be negative 1. And then for our other factor, we are going to have, we're going to set u squared equal to negative 1/2. And if we plug that into 1 over u squared plus 1, then we're going to get 2. So we're going to plus 2 over 2u squared plus 1 du. And then all we have to do is integrate, and so we're going to end up with negative inverse tangent of u, and then we'll go ahead and divide by 2 on the top and bottom here. And we can do our usual inverse tangent integration. So we're going to end up with square root 2 inverse tangent of square root 2u. I don't really have space for that, so I'll just write it on the next line. Evaluated at infinity and negative infinity. And for both of these inverse tangent terms, evaluating at infinity and negative infinity is going to be pi over 2 and then negative pi over 2, so overall both of these are going to be pi. So we're going to end up with our answer, which is pi times square root of 2 minus 1. Alright, so that's the simple method on how to solve this integral, but now we're going to jump into the more complicated method. And so there's some other identities that we have to go ahead and address before we start. So first, we're going to prove this simple gamma function identity. Gamma of n plus 1/2 is square root pi times 2n factorial over 4 to the n factorial. So first, we're going to start with gamma of 1/2 equals square root pi, I think, right? Yeah. That's just provable using the Gaussian integral. Then we know that gamma of x plus 1 equals x gamma of x, which means that gamma of 3/2 is 1/2 gamma of 1/2, right, which is equal to square root pi over 2. And we can continue doing this process, and we're just going to end up with 1/2 times 3/2 times 5/2 times 7/2, so on and so forth. So we can write that gamma of n plus 1/2 equals square root pi times, I'm going to use product notation from k equals 1 to n, right? Yep. Product from k equals 1 to n of 2k plus 1 over 2. I think that's right. Yes, that's correct. And you'll notice that if we, for example, plugged in n equals 2, we would be looking for gamma of 5/2, and we would multiply by 3/2, and then we'd multiply by, oh, I guess it should go from k equals 0 to n minus 1. So k equals 0 to n minus 1. And the only thing that we have to do is sort of simplify this. So we can see that this is going to be gamma of n plus 1/2 equals square root pi. We can switch this into pi n minus 1, k equals 0 of 2k plus 1 times the product of just 1/2. And so the product of 1/2, that's just going to be 1/2 to the n. Now this other product right here is actually just a it's actually a very common function which actually shows up a lot in power series, and it's what's called the double factorial. So I'm going to go ahead and talk about the double factorial because we're going to use it a lot. So n double factorial is 1 if n is 0 or -1, is 1 times 3 times 5 times 7, so on and so forth, if n is odd. And it's 2 times 4 times 6 times 8, and so on and so forth for n is even. And so that's going to be very helpful to us. So in this case, since we're summing up all the odd numbers up to 2n minus 1, yes, because if you plug in n minus 1 into the argument of the product function, then you'll see that the last one we're multiplying is 2n minus 1. This is just 2n minus 1 double factorial. We're almost done. Another important thing to note about the double factorials is that 2n minus 1 double factorial times 2n double factorial is equal to 2n normal factorial, because as you can see, as they line up right here, it's just going to end up, we can go 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, and we'll end up with just our normal factorial progression. So we're going to apply that right here. On the top, we'll have 2n factorial, and on the bottom, we'll have 2n double factorial. And this leads us to our last identity that we're going to be using, and that's that 2n double factorial is equal to 2 times 4 times 6 times 8 times 10, which, as you can see, pretty neatly matches up with just a normal factorial, because 2 is just 2 times 1, 4 is just 2 times 2, 6 is just 2 times 3. So this is actually equal to n factorial times 2 to the n. And so we're going to apply that right here. We're going to have on the bottom n factorial, and then 2 to the n, this is just going to become 4 to the n over here. And so as you can see, we've kind of shown that this is going to be our formula for gamma n plus 1/2. So now, it'll all make sense in a few minutes when we actually go ahead and do the integral. But we're going to find the Taylor series, or the Maclaurin series, I guess, for square root 1 minus x. The reason for this is we're going to get a sum that can be manipulated to look just like this Taylor series. So first, let's just go ahead and just find all the derivatives here. So we're going to start with square root 1 minus x. Then we're going to have negative 1 over 2 square root 1 minus x. And then now this is to the negative 1/2 power. So we're going to multiply by negative 1/2, but we're also going to multiply by -1 just because of the chain rule. So we're going to have negative 1/4 1 minus x to the 3/2. And if we keep repeating this, we're going to end up with negative 3/8, 1 minus x to the 5/2, negative 15/16, 1 minus x to the 7/2. All right. So if we go ahead and start writing out our Taylor series, the first term is just f of 0, which is 1. Then all the rest of the terms are going to be negative. So we're going to have negative, then this next one is just going to be x over 2 times 1 factorial. I'm just going to leave in the factorials because it's going to be easier to make our expression at the end. Then we're going to have minus x squared over 4 times 2 factorial. Then we're going to have minus x cubed, 3x cubed over 8 times 3 factorial. Then we're going to have minus 15x to the 4th over 16 times 4 factorial. And we're just going to continue so on and so forth in that way. Now the thing is, we have to be able to analyze all these terms right here. So I'm going to start by noticing that the first term is pretty different from the rest of them. So I'm going to leave that out of our expression for the Taylor series. And next, all we have to notice now is it's going to be 1 minus the sum from n equals 1 to infinity of x to the n over n factorial times something. So basically what we have to show here is what's being multiplied to make the derivative, right? So for the first derivative, all we're multiplying by is the first result of the power rule, which was 1/2. And then for the second derivative, we're multiplying by 1/2, and then we're multiplying by negative 1/2. And for the third derivative, we have 1/2 twice, and then... So as a result of the first differentiation, we're already dividing by 1/2. So we can put this 1/2 outside because all of them have that common 1/2. Then, after every successive differentiation after that, we're dividing by 1/2 again, and that's the result of the power rule, because we're multiplying by 1/2, then we're multiplying by 3/2, then we're multiplying by 5/2. So we can put a 2 to the n on the bottom here. And then we're going to need to include a double factorial, because when we're multiplying by 1/2, 3/2, 5/2, 7/2, that's going to follow the same pattern as a double factorial. So we just have to make sure to align it correctly. So for example, if we just put 2n minus 1 double factorial here, that would be incorrect, because if we were to plug in n equals 1 or n equals 2, then we would get 3 double factorial and we would be multiplying by 3 and then by 1. But that's incorrect because, as you can see here, there's no 3 in here because it's kind of shifted over by 1. So what we actually have to plug in here is 2n minus 3 double factorial. A lot of this is kind of just shifting things around until we're really sure that they work. So it is a little bit confusing. The result of putting in 2n minus 3 double factorial actually does match up. If we look at the x to the 4th term, which is when n equals 4, that's going to be 2n minus 3 is going to be 5 double factorial. So that's going to be 5 times 3 times 1, which matches the numerator of the x to the 4th term. So that's how we know that's correct. Next, in order to simplify this into easier terms, what we're going to do is multiply 2n minus 3 double factorial, and we're going to multiply it by 2n minus 2 double factorial. And we're also going to do this on the bottom, of course. Then the result of this is that this just becomes 2n minus 2 factorial because of that identity that we showed, because we're multiplying by all the even numbers and also all the odd numbers. All right, and 2n minus 2 double factorial is nothing but 2 to the n times n minus 1 factorial, because we're multiplying all the even numbers up to 2n minus 2 is the same as 2 times all the odd numbers, or times all the numbers up to n minus 1. So instead of 2 to the n, we'll have 4 to the n right here. All right. Now the only thing I want to do here is I actually want to shift the index of this. So we're going to just subtract 1 from the starting point to n. So that means on the inside of the series we're going to add, we're going to change all the n's to n plus 1. Because here n is starting at 1, but we want n to start at 0, so we need to add 1 to n everywhere on the inside. So we're going to end up with 1 minus 1/2, sum from n equals 1 to infinity of x to the n plus 1, 2n factorial over 4 to the n plus 1, n factorial times n plus 1 factorial. And just something I'm noticing right now, I have this for n plus 1, which means we'll end up with an 1 over 8 on the outside. I actually made a mistake earlier when I divided by 1/2 right here. That was actually incorrect. I should have been multiplying, and we should have a 2 there. So this should actually end up being 1/2. So overall, this is equal to square root 1 minus x. Oh, yeah, this should be just a 0. All right. So now let's jump into why we need this super odd sum in order to evaluate our integral. So this was our integral, and we're going to apply a few power series in order to evaluate it. So we're going to apply the power series for 1 over 1 plus x squared, which is just a derivative, or which is just a result of 1 over 1 minus x. This is equal to the sum from n equals 0 to infinity. Oh, I'm sorry, this isn't from negative infinity. This is negative 1 to 1 of negative x to the 2n, or negative x squared to the n. And so we're going to end up with interchange. I'm going to automatically interchange the sum and the integral. And also the other thing I'm going to do is I'm going to use the, just going to go 0 to 1 and multiply by 2 because we have an even integrand. So we're going to end up with the sum from n equals 0 to infinity of negative 1 to the n, the integral from 0 to 1 of square root 1 minus x squared times x to the 2n dx. Next, we're going to just do x squared equals u to the 1/2 equals x, dx equals 1/2 u to the negative 1/2. So we're going to end up with the sum from n equals 0 to infinity of negative 1 to the n times the integral from 0 to 1 of 1 minus u to the 1/2 times u to the n. We'll bring a 1/2 all the way out here, and then n minus 1/2. Now we're going to go ahead and apply the beta function. So for the beta function, we just need to rewrite this as 3/2 minus 1, and this as n plus 1/2 minus 1. And then beta mn is just going to be those numbers that we're subtracting 1 from. So 3/2 and n plus 1/2. So overall, we're going to have 1/2 times the sum from n equals 0 to infinity of negative 1 to the n times our beta function. So we're going to have beta m, which is just gamma, or we're going to have gamma m, which is gamma 3/2, gamma n, which is gamma n plus 1/2, over gamma n plus 2. All right? Oh, I'm sorry, this 1/2 should have canceled with the 2 from the beginning. I added an extra 1/2 here that shouldn't have been here. Okay, quickly, gamma of 3/2 is square root pi over 2 because it's 1/2 gamma of 1/2, and gamma of 1/2 is square root pi over 2. So we can just bring that outside as square root pi over 2. Next, let's use the formula that we proved earlier for gamma n plus 1/2. So that's going to be square root pi, which means we can remove this square root right here, times 2n factorial over, I believe it was n factorial 4 to the n. Yep, that's correct. And then gamma of n plus 2 is just n plus 1 factorial. So overall, we can say that our integral, which I'll call I, is equal to pi over 2s, where this is going to be s. So all we have to do is evaluate s, which I'm going to do on a new slide. All right. So now all we have to do is figure out what this sum evaluates to. And as you guessed, what actually happened to me while I was trying to solve this is I spent, like, I don't know, 3 or 4 days trying to figure out how to evaluate this sum. I plugged it into Wolfram and it gave me the answer, which I already knew because I had solved the integral the other way, but I could never figure out the method that was used to evaluate it until very recently. the past few days, I kind of figured it had something to do with the power series for the square root because I recognized the arrangement of the factorials, but I couldn't figure out exactly how to evaluate it until very recently. I kind of was playing around with the power series, and that's why I was deriving the power series in this video. So I'm just going to go ahead and remind us, square root 1 minus x equals 1 minus the sum from n equals 0 to infinity of x to the n plus 1 to n factorial over n factorial, n plus 1 factorial, 4 to the n, and all of this was 1/2. So you may notice if we plug in x equals -1, we will get square root 2 on this side, and then we'll get 1, and instead of minus, we'll get plus, because this n plus 1, so x to the 1 is just -1, times the sum from n equals 0 to infinity. So no, I'll leave this minus sign here to show you why that works. We're going to get -1 to the n plus 1, and so we factor out -1 to the 1, and that'll become a plus sign. And then we'll have 2n factorial over n factorial, n plus 1 factorial, 4 to the n. And you may notice that this is actually just s. So we can write that square root 2 equals 1 plus 1/2 s, which means that square root 2 minus 1 equals 1/2 s, and s equals 2 times square root 2 minus 1. This means that I equals pi over 2s equals pi times square root 2 minus 1. So overall, this method for solving the integral is definitely not the fastest and easiest method, but it is one that's relatively easy to at least get to the sum and figure that much out. I had a ton of fun using this method. It was just really amazing when you're playing with the numbers and you get this crazy series, and then you spend a few days just trying to solve that series. So I had a lot of fun with this integral. Probably the best way is to use the first method that I showed you guys, but I think that it's always fun to go on these wild goose chases and find these crazy sums and integrals that you don't even know if you're going to be able to solve, but then eventually you have some insight, you have a moment of truth, and you really just figure out how to solve them. So I hope you guys enjoyed this video. If you watched through the whole thing, wow, I'm surprised. I didn't think anyone would. Yeah. Thank you so much for watching, and I'll see you in the next video. Hope you enjoyed.